So thank you, Ben.
Hey, thank you for the invitation, Greg, and it's nice to meet and see all of you virtually. Um, this talk is primarily based off of one that I gave at the DPP in the low temperatures session. So if you attended that, my apologies for rehashing old material, but I have a few updates in light of recent work that we've done. So broadly speaking, my research interests include plasma propulsion devices. These are technologies which are intended for fuel-efficient transport in space, and that stems directly from the fact that they have very high specific impulse or exhaust velocity in contrast to things like chemical engines. But related to that, I've also done quite a bit of work in low temperature plasmas, specifically in the field of turbulence and non-classical transport. And it turns out that these two disciplines actually have quite a bit of overlap, particularly in the context of one of the most popular types of electric propulsion flow, which is the Hall effect thruster. So it turns out that despite the fact that this device is, at this point, the most widely flown type of thruster in space, there are pieces of how it operates, its underlying physics, that remain poorly understood, most notably related to questions about the internal electron dynamics. As it turns out, in the past 10 or 20 years, there have been quite a few advances that have shed new light onto what causes the electron dynamics to change in the way they do. And it's now believed that it's fundamentally linked to the existence of the onset of electrostatic turbulence at a low level. So a lot of the work that I've been pursuing in the past couple of years that I'll focus on this talk is trying to characterize experimentally the role of that turbulence and in turn leverage that experimental insight into new theoretical and numerical capabilities for developing new predictive tools for Hall effect thrusters. So with that introduction in mind, here's kind of a quick overview of electric propulsion writ large. You can see here it's characterized by an external power supply, invariably solar now, though there's some talk of putting nuclear in space in the next 10 years. And it takes that external power and then converts it into directed kinetic energy by first ionizing a neutral gas. Usually we use something like xenon or krypton, and then applying a combination of electric and magnetic fields to accelerate to high speed. So most of the modern systems that are flown are primarily electrostatic in nature, relying just on a strong potential drop applied to accelerate the heavier species, the ions, to a preferred direction. The resulting velocities that you can achieve are up to an order of magnitude higher compared to traditional chemical rockets, and that translates directly to substantial savings in terms of fuel economy, to the point that with Hall effect thrusters, or broadly speaking, any EP systems, you can achieve the same types of impulsive maneuvers in space as you would do with the chemical rocket, but with a fraction of the fuel, sometimes 20 or 10% of the actual fuel requirements. So these types of savings translates to substantial savings in launch cost and propellant cost for the mission. The Hall effect thruster is a particular flavor of electric propulsion, which is at this point the most widely flown type of EP that's largely been supported by or buoyed up by the action of SpaceX. All of their Starlink satellites have a Hall effect thruster on board. And you can see kind of the major selling points or advantages shown in bullet point here. They have relatively high thrust density, which means you can produce more force per unit area, high specific impulse or exhaust velocity, and they have flown without incident for several decades at this point. And indeed, to that point, they're widely used for geostationary applications, for Starlink to do drag makeup, and they've been baseline for some upcoming robotic missions, including Psyche, which would be a mission to a protoplanet that's meant to launch in the next year, and the Deep Space Gateway, which is intended to be a space station which will be anchored around the moon. Beyond that, in particular in Michigan, we're interested in exploring the operating envelope of Hall effect thrusters to new regimes. Specifically, to give context, most Hall effect thrusters that are flown to date have been demonstrated at about 4 kilowatts of power, which is sufficient for orbit raising and station keeping for robotic applications, but insufficient for crewed exploration. If you wanted to enable rapid transits to Mars, for example, you need megawatt levels of power. So that invites key questions about how you scale up the technology to accommodate those higher levels of power and commensurately higher levels of thrust. And hand in hand with that goes the question of, once you develop this technology, how do you undertake rigorous qualification efforts to ensure that the technology will survive its flight out to Mars or beyond? So with that in mind, modeling and simulation tools are absolutely critical to the future of this technology. I would say it's fair that for the most part, up until the early 2000s, most Hall thrusters were developed largely without the use of computational tools. But now as we try to push their operating envelope to new lifetimes and new operating regimes, there's an increasing need for these types of simulation tools to promote qualification efforts and to cut down on cost of those qualification efforts. With that being the case, I think it's broadly speaking fair to say that there's no such thing as a fully predictive Hall effect thruster model. We're not in a situation now where we can program up in a commercial code a model for a Hall effect thruster, given its notional geometry, run that code and be confident that the model predictions will be truly representative of its performance. And the reason for that, as is the case with many types of plasmas spanning the range of density and temperatures, is that there's aspects of the operation of the system and the underlying physics that remain poorly understood. The most dominant one in the context of Hall effect thrusters is the existence of anomalous cross-field electron transport. So with that kind of introduction in mind, and to set the stage for the rest of this discussion, I have kind of these 3 bullet points that I want to touch upon today. The first is defining what I mean when I say anomalous electron transport in Hall thrusters. Second is a discussion of what our current understanding is of what causes that transport and what we've done to try to improve that understanding from an experimental and theoretical perspective. And 3, how have we recently been trying to leverage that understanding to develop predictive tools which can address this first question outlined here, which is, can we develop the M&S tools which can enable expanding the operating envelope of Hall effect thrusters? So let's start with the first question, which is the problem of anomalous electron transport. To that end, I'm going to walk through at a high level the principle of operation of a Hall effect thruster, and this will set the stage for
Benjamin John.
Sorry?
I think that was just an accidental noise.
Oh, okay. All right. So I'm going to talk about a high level, the operational Hall thruster, and this will help motivate our discussion of the physics here. So I'm showing a 3/4 view on the left-hand side, and then an example of a Hall effect thruster firing on the right-hand side. These devices are characterized by being axisymmetric with respect to a central center line, which passes through the center of the thruster, and they have this characteristic discharge channel, which is kind of a donut, typically made out of a ceramic material like boron nitride. Inside the channel, there's an upstream red anode and then a downstream cathode, which serves to terminate the potential, which is applied across the channel. And in turn, there are strong electromagnets, which are embedded both in the internal region, that kind of gray internal region, and the external outer pole region, which provides a transverse magnetic field across that discharge channel. So to talk about its principal operation, I'm going to show it here in a cross-sectional view, and there's the 3/4 view on the right-hand side again, give you a sense of the 3 dimensions of this, 3-dimensional nature of this device. So the first step is we heat up a thermionic cathode, which produces electrons, which is shown here. Then we apply an electric potential from the upstream anode to that cathode, generating an electric field, which is shown as those green arrows. That electric field serves to pull electrons into the discharge channel, completing the circuit. The next step is to apply, in the canonical sense, a transverse magnetic field, which is tailored in such a way that the electrons are magnetized, whereas the ions are not. And as a consequence of the cross electric and magnetic field configuration, the electrons undergo their Larmor precession, but at the same time undergo an E cross B drift in the azimuthal direction. Since this is an E cross B drift, it's a Hall effect drift from whence the thruster derives its name. So that kind of characteristic electron velocity drift in the azimuthal direction, moving at several hundred kilometers per second, is an indication of the Hall effect drift, which is critical to the operation of these systems. As a next step, we flow in neutral gas, which is shown as xenon particles here, through a manifold which is embedded in the anode. That neutral gas then transits the gauntlet of the electrons, which are undergoing their Hall effect drift, leading to impact ionization, then resulting in the plasma state. At this point, quasi-neutrality is preserved, so this avoids kind of space charge limitation effects, which are endemic to ion thrusters, and limits their thrust density. But at the same time, we tailor the magnetic field in such a way that the ions are unmagnetized, whereas the electrons are magnetized. And as a consequence, on the length scales of the thruster, the ions do not experience that magnetic field and only respond to the electrostatic force. So they are subsequently accelerated out of the geometry of the thruster as shown here to speeds which are dictated by the potential drop applied between the anode and cathode. In order to preserve neutrality, then additional electrons are sourced from that cathode downstream and maintains the overall thruster and consequent spacecraft neutrality, generating thrust from the acceleration of the ions, which is neutralized by those downstream electrons. So in terms of advantages, this device, because it's quasi-neutral, as I alluded to earlier, can produce relatively high thrust densities, high thrust per unit area. And at the same time, because its acceleration of the ions is directly linked to that applied potential, it has variable exhaust velocity and specific impulse, which in turn translates to the ability to save in terms of propellant mass budget for your spacecraft. All right, so with that kind of principle of operation in mind, I'm going to now focus in on talking about the problem of anomalous electron transport in these devices. And to that end, I will zoom in on the dynamics that are going on in this region characterized by the cross electric and magnetic field. So to motivate the problem of anomalous electron transport, let me start with what the idealized description is of the electron dynamics, which is shown here. And in principle and in collisionless plasma, those electrons would be trapped indefinitely in these in azimuthal drift. So I've lost the three-dimensional element here, but just envision those electrons undergoing Larmor precession as well as in azimuthal drift into and out of the page, circling around that discharge channel. In practice, classically, those electrons will not stick to those magnetic surfaces indefinitely. They can collide into heavier particles or even the walls. And that can lead to them being perturbed from their orbits and actually following the electric field or anti-parallel to the electric field, leading to a transverse current. And that's what's exhibited here. We, of course, can calculate based off of classical closures what the effective transport should be subject to these classical effects. And that's kind of what's shown here is this trickle of electrons. In practice, however, when we actually go to measure the electron current exhibited by these devices, we see that the degree of electron current across field lines is several orders of magnitude higher than you'd anticipate classically. So this suggests that this kind of classical interpretation of particle with wall or particle with heavier species collisions leading to electron transport is not actually representative of the underlying physics. So broadly speaking, this is the so-called anomalous problem of an electron transport in Hall thrusters, which is there is some mechanism which leads to this enhanced transport. And to date, this has not been sufficiently well understood that we can develop first principles predictive models for Hall thruster operation. So there it is, answer to the question, what's the problem of anomalous electron transport? Is that the current is orders of magnitude higher than would be classically anticipated. So with that question in mind and kind of framing the problem, in the context of developing a physics-based understanding and from a more applied perspective, a modeling and simulation tool that can be applied predictively to Hall thrusters, the next question is what effectively causes this anomalous transport? And so I won't go into the details of each of these hypotheses, but broadly speaking, over the past 50 or 60 years of Hall effect research, these have been the leading contenders. One, which is electrons pick up effective enhanced cross-field transport through collisions of the walls. One is borrowing heritage from the high energy density plasma community, which is it can be explained by low density fluctuations, which are broadly captured by Bohm diffusion. Or third, it can be explained by the onset of either large scale or incoherent turbulent instabilities. So with these kind of hypotheses in mind, there's been quite a bit of work experimentally and theoretically done over the past 50 years to look at each of these mechanisms. But I would say that particularly in the past 20 years, instabilities have risen to the fore or come to the fore as the dominant mechanism, which is believed to explain the transport. So I'm going to talk a little bit physically about how instabilities can lead to that at a kind of phenomenological and intuitive level, and then I'll talk a little bit about the theory behind that. So qualitative description for how that contributes to the mechanism. First, as I alluded to earlier in the principle of operation for the Hall effect thruster, the E cross B drift serves as a very strong source of energy for the onset of instabilities, a free source of energy. So that's exhibited here by this blue curve, the induced motion of the electrons. In turn, that energy that's present in that drift can lead through collisionless processes to the onset of instabilities through resonance coupling, for example, or even through in the unmagnetized limit inverse Landau damping. And in turn, that can lead to the onset of momentum and energy propagating in the same direction as the Hall effect drift. So that's what's shown here qualitatively as the onset of these kind of green oscillations or perturbations in plasma density and potential. The onset of these waves does not come for free. They have some momentum associated with them. So the growth of momentum in the waves comes at the expense of momentum in the electrons. And from the kind of fluid description or perspective of the electrons, that appears as an effective drag acting on that species. So that green arrow, though, represents kind of an effective anomalous force. And then again, through just a F cross B consideration, that azimuthal force can give rise to an effective drift, which is in the transverse direction. So the takeaway from this is that the onset of instabilities driven by the Hall effect drift can lead to an effective drag force in the azimuthal direction. That drag force in turn can be thought of as an effective collisional force, which in turn promotes enhanced cross-field transport.
Then how collisional are these plasmas? Is the mean free path much longer than the gyro radius?
Yes. Yeah. So in terms of effective Hall parameter, which is how we usually tend to couch it, the Hall parameters in these devices on the order of 100. So the ratio of cyclotron frequency compared to collision frequency. But I should say that that's the effective Hall parameter. From a classical perspective, the Hall parameter can be as upwards from toward 1,000 when you compare it to classical collisions.
Okay, thanks.
Yeah. Okay. So with that kind of physical description in mind, let me turn to these questions related to the instability, which is what types of modes can actually be driven in a Hall thruster, what's actually resonant with those plasmic conditions. Then the all-important question, even if we expect those to exist from a theoretical perspective, do they exist? And then finally, the most critical one from an experimental perspective is, can they in fact explain the transport, even if they do exist? So the first question was largely addressed through numerical simulations. And this is actually what kind of kicked off a renaissance in looking at transport, in my view, in Hall effect thrusters in the early 2000s, which was this paper by Adam and Jorns, who did a two-dimensional PIC simulation for a reduced dimensional perspective of a Hall effect thruster. So that's what's shown here on the right-hand side. I've zoomed in on a quarter view of the discharge. And this is just a snapshot in time of the spatial distribution of density fluctuations that are predicted from their two-dimensional PIC code. And the takeaway that came from this code is that indeed, if you do have an imposed Hall effect drift, it can lead to the onset of small-scale structures which are propagating in the azimuthal direction. They've done subsequent work to try to understand what these types of modes are, but the immediate takeaway from this is that, as you'd anticipate, if this kind of free energy source exists, there are types of waves that can be spontaneously onset. So subsequent analysis, which largely follows that paper trail I'm showing on the left-hand side of the page, has looked into what, from a linearized theory perspective, instabilities could exist under these operating conditions. And the consensus has largely been that these types of waves are probably a form of electron-cyclotron drift instability. So I'm showing the real dispersion for that on the right-hand side, subject to different assumptions about the parallel component of propagation. But the takeaway here is that its dispersion exhibits an increase in frequency as a function of normalized wave number in the azimuthal direction. And the wave in turn is characterized by cyclotron resonances, which I'm defining here as wave numbers that are commensurate with an integer multiple of the cyclotron frequency divided by the electron azimuthal drift. So the takeaway is that when you do a linearized theory approach to looking at the plasma conditions in the Hall effect thruster, you do conclude that there's positive anticipated growth for the electron-cyclotron drift instability. And indeed, when they go to look at these numerical simulations, they see that the dispersion is commensurate with that. Okay. So that was kind of the numerical clue, which then kicked off an equally difficult question of how do you actually determine if these instabilities exist? And this is a particularly difficult one because the dominant wavelength that's predicted for these ECDIs is anticipated to be on the order of millimeters or submillimeters. And that can be quite challenging to detect from a probe with using probes. So indeed, the first actual demonstration of ECDI was not done with probes. It was innovated by Professor Sadina Sagata, who was at the time at CNRS and now since has moved to Georgia Tech. As part of her dissertation work, she did this nice diagnostic where she used coherent Thompson scattering to resolve the dispersion relation for instabilities in the azimuthal direction for a Hall effect thruster. So you can see here the dispersion, which was the lower bound in the detection limits here, was inverse radians about 5,000 millimeters. So they actually weren't able to look at wavelengths much larger than a couple millimeters. But you can see here that the dispersion is clearly linear. And if I take a step back and I contrast that with this theoretical dispersion, you might say, well, these are actually not the same wave. And indeed, that did kick off an interesting discussion for a couple years. But more or less, the consensus seems to be that this seems to be the ECDI, but the ECDI in the limit that you have finite parallel wave number actually starts to look much like an acoustic wave. So this is actually totally self-consistent with the theoretical linearized dispersion that's been proposed to date. So key takeaways from this finding are that they actually found the wave. It's consistent with the numerical simulations in so much as the dispersion is consistent. But there were some interesting notable departures from simulation. Foremost among those is that the spectrum of oscillations appeared to be incoherent and turbulent, characterized by an inverse power law decay. And this had not been predicted from simulations. Simulations instead had shown that the wave should be relatively coherent and dominated by one length scale. So that actually is still something that has not quite been resolved in the community, this disparity between experiment and simulation. But at least from the perspective of the linearized expectation that there should be this type of instability in the plasma, that was confirmed experimentally. So that's kind of where previous work leaves off. And then where we started to pick up the torch was trying to expand on this result and ask the important question. Well, it's clear that these instabilities exist and are expected to exist in the plasma, but that's a far cry from actually saying that they can explain the transport. And while numerical simulations, particularly these reduced dimensional ones, would seem to suggest that indeed the existence of the instabilities, once you do a correlation between density and potential fluctuations, should be able to explain the enhanced level of electron transport observed in these devices. This had not been experimentally verified. And there are reasons to think that maybe there should not actually be parity between experiment and simulation, in addition to the things I just mentioned. For example, often these simulations predict that the amplitude of waves are much higher than what had been experimentally observed before. So this is kind of the natural question where we started to take a look at it from our perspective here in Michigan. So to go after that experimentally, I'm going to talk a little bit about the theoretical framework that we developed to try to address this question. And then talk about some of the measurements at a high level that we did to go after that question. So first, this is just a recapitulation of what I said earlier, and that is that the effect of the waves can be interpreted as an effective drag force in the azimuthal direction. And in turn, we take the additional step, and this derives its heritage from kind of how they do fluid-based models of Hall thrusters right now, which is to represent the effective transport with an ad hoc or anomalous transport coefficient, which in this case is an effective collision frequency that's denoted there as nu sub an. So the major implication of this expression is that in formulating in this way, we have some characteristic azimuthal current denoted as J sub E, and then that scaling coefficient denotes the degree to which anomalous transport is occurring, in turn leading to an enhanced azimuthal force and by extension cross-field electron transport. So with this kind of formulation in mind, the first question we wanted to ask is, can we use this type of formulation coupled with direct experimental measurements of the electron properties and ion properties in the thruster to back out what the effective transport coefficient should be? In other words, can we in some way directly measure what that anomalous transport is and a transport coefficient is? And this is critical because it's necessary for establishing the kind of experimental ground truth for comparison against theory, as well as subsequent experimental measurements that we take. So with that in mind, this is some work that was done in conjunction with my former student, Ethan Dale. We were able to apply a methodology which is based off of laser-induced fluorescence, combined with some far-field probing measurements to actually back out and directly measure from this effective Ohm's law what the Hall effect anomalous collision frequency should be. So First, I'm showing here as a function of position in the thruster. And to orient you, it's showing positions along the channel center line as a function of axial position. So we're working away along that blue line. And on the bottom axis here, it's just a normalized position where the vertical lines denote the exit plane at 0 and the location of peak magnetic field at about 0.3. So the green curve shows the cyclotron frequency from the applied magnetic field. The red curve shows the experimentally measured classical collision frequency. And then finally, this is the measured anomalous collision frequency, which corresponds to nu sub an over there. So kind of the major implication from this result was that we were indeed able to measure in situ the effective collision frequency transport coefficient. We were able to confirm that it's orders of magnitude higher than classical, and we were able to show that it has this kind of characteristic spatial dependence. And I will make an aside here, which is that when you use these kind of spatial dependence for transport coefficient in Hall thruster fluid codes, if you just impose this type of transport profile, it actually matches experiment quite well. All right, so that's kind of the experimental result and helped establish the baseline. The follow-on question was, can the existence of ECDI actually explain the transport, explain these trends in the curve? So to address that question, we actually had to go and take a closer experimental look at what's going on with the plasma turbulence associated with the ECDI in the thruster. And in turn, through just quasi-linear theory, you can come up with a formulation for how this transport coefficient should vary as a function of the properties of the waves. So that's what's shown here on the right-hand side, where it's an integral over the frequency spectrum of the waves. And there are kind of two contributing factors. One is the energy which is present in the waves, and that's represented by the ratio of phi, which represents potential amplitude of the waves compared to the electron temperature squared. And it's intuitive that if the wave turbulence spectrum has more energy associated with it, we would expect that it could act as more of an effective drag force on the electrons. The second contributing factor is represented as gamma sub E, and this is the rate at which the electrons extract energy or momentum from the background, the rate at which waves extract background momentum from the electrons. If that is a higher value, in turn, we'd also expect the effective transport should be higher because it's able to extract momentum for a given energy at a higher rate. So kind of with this quasi-linear expression in mind, that the next experimental question is, can we experimentally characterize these properties and in turn relate them back to the empirical profile that we measured? So that sets the stage for the next discussion point, which is how do we measure these properties? So I mentioned earlier that it's difficult to do these measurements with probes, especially it's difficult to measure dispersion with probes because they run into aliasing effects. So the wavelengths are too small to be unambiguously characterized with kind of a two correlation technique. So instead, to address that first question of what the power spectrum is, we actually just shot one biased ion saturation probe into the thruster channel. And that's what's shown qualitatively here. So I have a Langmuir probe, biased ion saturation limit, which is shot along the channel center line into the discharge and measures fluctuations in the oscillations in ion saturation current, which then for the ECDI, we can assume, provided the electron temperature doesn't fluctuate very much on the timescale of the oscillation, scales linearly with the variations in plasma potential. And here's what the results look like. So I'm going to show the power spectrum as a function of frequency and for a couple different spatial locations. So this is color coded, but this follows the same convention that I had earlier, and that is Z over L denotes distance from the anode as a distance from the anode normalized by the length of the channel itself. So blue is closest to the anode, and then we make our way progressively downstream going to purple. And the takeaway from this is that the power spectrum, focus on one color, purple, for example, is extraordinarily rich, and it's characterized by a number of different oscillations. The first dominant peak, actually, which occurs at about 50 kilohertz, is the so-called breathing mode oscillation of this thruster. And that's kind of a larger scale ionization related mode, which is a longitudinal and therefore probably not linked to transport. But from our perspective, the more interesting content starts at around 10 to the 5th hertz and then has that kind of inverse decay moving all the way out to 10 to the 7th. And this we've been able to show is correlated with the existence of electron-cyclotron drift instability. And indeed, if you look at all those kind of red dashed curves, those are commensurate with the cyclotron resonances, which are predicted from linear theory. So the takeaway was that we were able to measure just from this ion saturation probe the power spectrum of oscillations, which is one of the key pieces of information for evaluating the transporter. Now, a broader and interesting question is how does energy get transferred across frequency and length scales in this system? That's still an active area investigation, but we've been able to show, among other things, that it's probably can be attributed to wave-wave coupling effects. Okay, so that was how do you measure the energy in the waves? The next question is, how do you measure the effective rate at which the waves extract momentum from the electrons? That's that gamma E parameter. So in this case, we actually did use a 2-correlation probe technique, and that's shown qualitatively here. We set up 2 probes, which are spaced in the azimuthal direction, and then we measured the fluctuations in ion saturation current as a function of time, and effectively looked for correlations between those two. This is a pretty standard technique for inferring dispersion of waves, kind of looking at the characteristic time it takes for oscillations to propagate from one location to another. But it turns out that if you're careful with how you look at different higher moments of the correlations, there are established techniques for how you can back out things like the effective azimuthal growth rate of instabilities in that direction. So this is kind of elaborating on that point where we look at the oscillations in those directions. And then from those 2 oscillations, we can take various moments or cumulant moments. So that's shown here on the left, on the lower part of the curve. So blue, for example, would be location X, Y would be a location which is spatially separate from that in the azimuthal direction. And the ensemble average of X with its complex conjugate just gives the power spectrum amplitude. Same thing for Y. We can look at the cross correlation between those, and then we can look at bispectral moments as well, XX star, Y star, and XX star, YY star. So this is all information that can be experimentally gleaned from these 2 probes. And the reason why it's relevant is that there are established methods based off of the techniques of Ritz and Kim, where effectively you can start with a kinetic governing equation for the propagation of waves, which includes both linear effects as well as nonlinear effects. And captured in that equation includes things like the growth rate as well as nonlinear length scale transfer rates. And so if you have these experimental measurements at 2 locations and the subsequent calculated cumulants up to 4th order, you can substitute all those values in and actually develop a system of equations which closes for the linear growth rate and the nonlinear transfer rates. So in the interest of time, I didn't actually include those equations here. The initial details of that technique are elaborated on in those papers from 1989 and 1996. And most recently, we had a paper come out in PRL where we talk about adapting those techniques, which were primarily derived in the spatial Fourier space to time-based Fourier space, which is more appropriate for these small length scale plasmas. So I'll invite you to review the paper. My student, Zach, is in the process of writing his dissertation, which has exhaustive detail on the methodology. But for now, if you'll take my word for it, the sets of equations close, which allow you, in effect, to determine the effective things like the linear growth rate from these 2 cross-correlation probe measurements. So with that being said, we were actually able to put those probes in the plasma and measure the linear growth rate in the azimuthal direction. And that's what's shown here. So this is a direct physical measurement of the degree to which the waves are extracting momentum from the azimuthal direction in the plasma. And there's some interesting features that pop out from this. First and foremost is that there are actually cyclotron resonances here. This is to be expected theoretically, which is that the ECEI gets its energy from the cyclotron resonance effect, and that's directly represented here by this experimental measurement. So we anticipate that we'd have positive growth rate here. Interestingly, we actually see some damping that occurs at low frequencies. The reason for this is not clear from linear theory, but could be attributed to things like the existence of collisions, or just the fact that at those relatively long length scales or low frequencies, inhomogeneous effects may lead to damping or cutting off of the waves. Right. All right, so from the perspective of answering the question, what is the anomalous transport? We actually have the tools now and experimental measurements that are disposable to directly evaluate what that transport coefficient should be. So we can take those measured linear growth properties, we can take the power spectrum as measured on the right-hand side, we can combine those and integrate over the spectrum, and we get a result as a function of experimental position for what the anomalous collision frequency should be. So again, there's the classical result, which is shown in gray as a function of position, origin magnitude small, too low. And then in the purple curve, we have, this is the measured with that technique I alluded to earlier. So this is directly measured from an effective Ohm's law and that LIF technique. And then using our wave-based measurements, the kind of pink/purple curve is what we'd expect the turbulence to contribute to in terms of cross-field transport based off that linearized theory, coupled with quasi-linear theory coupled with our experimental measurements. So the major takeaway from this is that those two curves within experimental error overlap. And this to us served as a strong indication that indeed the existence of turbulence in these thrusters is sufficiently strong combined with the effective measured growth rates to effectively explain this cross-field transport coefficient. So this is one of the first direct measurements of this type to our knowledge, and of course it comes with many caveats. Foremost among those is the fact that we had to use probes to do this measurement, and probes can perturb the plasma. But at least as a first initial proof, it seems like we are within less than an order of magnitude to explain the measured transport. Okay, so the last thing I want to talk about is that if we've proven to ourselves and are willing to accept that the transport can be explained by the existence of ECDI, that the last practical question is, can it be modeled? And can we leverage our experimental understanding to model it? So to give some context to this, because the ECDI is inherently a kinetic wave, in principle, you actually need fully kinetic codes to capture its onset and interaction with the waves, which leads you to architectures like PIC or reduced dimensional blast-off simulations. But from an engineering perspective, those are not particularly useful because the run times are too long and they're often tend to be reduced dimensional, have reduced dimensionality. So I would say the more industry standard right now is that we use fluid-based codes in which we effectively try to represent this transport through an ad hoc coefficient, which can be tuned to match experimental data. But of course, this is not predictive because that transport coefficient is not known from first principles. So that's kind of represented here where the fluid-based formulations are kind of captured by these broad equations here. And then in Hall effect thrusters, usually just use a diffusion transport equation for the electrons, neglecting their inertia, and capture the effect of the anomalous transport as this coefficient which can be tuned. In order to make those equations closed and self-consistent, though, the major theoretical ask is to try to find a closure equation which represents that effective transport coefficient in terms of fluid properties. And indeed, our overarching goal is to try to see if there are ways that we can leverage our experimental insights to motivate some theoretical expressions for what that closure might look like. So there's been quite a bit of work on this in the past. Not a lot of it informed directly by experimental measurement, more informed by drawing parallels from other communities or even data-driven methods. But you can kind of see notionally what those closures look like. You have Bohm scaling, or you have transport scaling, which is based off of assuming eddy turnover to viscous effects. So it actually draws parallels from classical turbulent fluids. But I guess I'll end this segment here with the comment that despite many different closure models that have been proposed to date, none of them, when they're self-consistently implemented in fluid codes, is actually able to predictively estimate performance. So an alternative approach that we've been pursuing in Michigan is to try to leverage these experimental insights to see if there's an appropriate closure. So I'll spend my remaining few slides kind of talking about that. And with that in mind, we can leverage these experimental results to make some simplifications that may ultimately drive at a simplified closure. So for example, we see that this collision frequency is actually integrated over the entire power spectrum. But one way we might be able to simplify it is to ask the key in question, is there a dominant length scale where the actual energy exchange occurs with the background electrons? And if that's the case, then that may allow us to effectively neglect the interactions with other waves, and therefore translate this integral over frequency space or wave number space to one that is just evaluated at one frequency or wave number. So indeed, if we actually look at the rate of energy absorption of the waves from the background plasma, we see that there's actually just one dominant length scale where that occurs. And that dominant length scale is commensurate with the first harmonic of the cyclotron frequency. So this is a key indication that we can simplify this integral quite substantially by only taking into account the contributions for energy exchange at that length scale. So flipping back and forth here, we go from that integral to one which is just proportional to that energy exchange at that dominant length scale multiplied by the amount of energy present in the spectrum at that wave. And again, to harken that back to kind of physical intuition, that should hopefully make sense, because that is where those cyclotron resonances are where the wave is pulling its energy out of the electrons. The second question from a closure perspective is how much energy is actually present at that length scale. And indeed, there are a number of different kind of saturation processes that have been proposed to date, ranging from the Fowler limit to just simple thermal saturation limit, or things like the existence of ion trapping. But kind of an intuitive one is to make the onsets that the maximum of energy that the electrons, that the waves can pull out of the plasma is going to be commensurate with the thermal energy. And indeed, we've gone in and measured the ratio of energy at that max frequency compared to the thermal energy. And we found that it varies with less than an order of magnitude. So just by a couple of factors, the wave energy always seems to be commensurate with that kind of saturated limit. So that allows us to make the additional assumption that perhaps we can eliminate that term entirely, assuming phi goes like the thermal energy, and then we just recover that the anomalous collision frequency should go like that energy of a rate of extraction or momentum from the background plasma. So the last question is, what is that value? And the first thought might be that we could use existing linear theory for what that value should be. But our experimental measurements have shown that the linear theory is a far cry from the actual experimental measurement. And this is probably because a lot of the assumptions that go into linearized theory predictions for growth rate are violated, including the fact that we anticipate that the electrons are probably not thermalized in these plasmas. So it kind of invites into question, how do you model that effective growth rate? And one thing I'll just point out from this slide is that when we do these measurements, we can contrast the linear growth, which is shown as the black curve, and the nonlinear growth, which is shown as the dashed curve. And we can marry that with kind of an additional term which takes into account the rate of convection of wave energy in the plasma. And the takeaway from this is that just doing an energy balance, we can make arguments that the rate at which the energy is extracted from the background plasma is directly balanced by the rate at which the waves propagate out of a given differential volume. So to say that again, at steady state, the rate at which electrons pull inertia or energy out of that background species is directly balanced by the rate at which those electrons propagate out of the geometry. And so if you make that onsets, then the one potential closure is to assume that growth rate scales like the rate of convection of wave energy out of the plasma, which, as we already established, the wave energy scales approximately thermally. So this is one closure model that we've tried. We've tried some other ones which are kind of informed by the onsets that maybe the rate of linear extraction is balanced by nonlinear energy transfer scales to much larger wavelengths and smaller frequencies. But I'm going to show this one because it's had the most promising results to date. So we've actually put in this closure, and the follow-on question is when you use that closure and you put it self-consistently into a fluid code, how does it behave? And to illustrate that, first I'm showing the collision frequency as that's used in a in a Hall effect thruster code right now. This is a code that's developed by JPL. And you can see it kind of has that characteristic dependence I showed earlier, where there's an increase and then a decrease in collision frequency followed by an orders of magnitude increase. And the first test we can apply is if we use the outputs of this code in terms of temperature and ion velocity, and we substitute those into this closure model on the left-hand side, how does it compare? And that's what's shown as this gray dashed curve. So it actually captures some of the nice features of this, which is orders of magnitude change in values for the collision frequency, and kind of captures this characteristic minimum here, which is usually coincident with the peak electric field. So it's definitely not quantitatively correct, but subject to the many simplifying assumptions that have gone into it, this would seem to suggest that it's getting kind of physically qualitatively correct behavior. So the follow-on extension is, how does this do when we self-consistently incorporate into the code? And indeed, if we take that collision frequency closure model and put it into a NASA code where we replace that transport coefficient with this simple closure model, we have what's shown here on the right-hand side. So black is the kind of experimentally measured collision frequency transport profile, and then the dash curves represent the self-consistent result when we self-consistently implement that closure model. And the takeaway is that it doesn't get the physics right. The transport profile is displaced downstream, and the magnitude is not nearly high enough, but it is getting some qualitatively correct features, most notably the fact that it exhibits a minimum. So we will not say this is a solved problem by any stretch of the imagination, but it has been kind of a promising initial result showing how we can leverage experimental measurements to start to inform closure models that are can capture qualitatively, if not quantitatively, correct behavior. And indeed, since presenting these results just a couple of months ago, we've been doing a lot more iteration, both experimentally and through fluid-based closures. And we have some newer closure models that we think might even be more promising. So to that last question, can it be modeled? Well, it turns out this 50-year-old problem is still not quite solved, and we continue to work on it along with many of our peers across the community. But it's, I think we're making good inroads by kind of taking this approach where we leverage experimental insight to inform our models. So to kind of wrap up here, Hall effect thrusters are widely used, but despite that wide use, there are still open questions about how they operate, specifically linked to their electron dynamics. Recent work has seemed to suggest that the existence of turbulence is fundamentally linked to those electron dynamics. And we've been trying to improve that understanding through experimentally and modeling-based efforts, with the ultimate goal of being able to develop closure models which are sufficiently high fidelity that we have a measure of predictive capability. So I'll bring to a close here just by mentioning all the students and former students that have supported this work that are shown here on the left-hand side. And there's a picture of my lab group on the right-hand side. And a lot of this work was supported by a combination of the FSR Young Investigator Award and the DOE Early Career Faculty Award. So I left about 10 minutes for questions, and I'd be happy to answer those at this time.
Thank you very much. Okay, let's open the floor to questions.
Yeah, I've got a question. Thanks for a nice talk. So these millimeter length waves in the ECDI instability, are those overlaid on top of the longer wavelength spoke modes that you see in the device as well?
Yeah, they are overlaid and they can be correlated. So the spoke modes, azimuthal waves, the spoke modes don't exist in a lot of the thrusters that I work on. And we work primarily in what are called shielded thrusters, where the magnetic field topology is designed to kind of maintain high electric potentials along the walls. And that has a second consequence of kind of displacing the plasma a little bit downstream. And we actually don't see those rotational spokes for the shielded thrusters. But when they do exist, yes, they've been shown to be correlated. And the ECDI is also correlated with the breathing mode oscillations, those large-scale longitudinal oscillations I alluded to.
Okay, thank you.
I have a question.
Sure.
Can you say what you need to know about electron transport to predict thruster performance? So you showed some graphs, for example, of effective collisionality versus Z. if you knew that curve, could you predict performance, or do you need, is this just an indication of how well your closure model gets this, can get the anomalous transport, but you still need to do a 3D simulation, for example, with that?
So from a fluid code perspective, you need the closure model to satisfy two requirements. One is that it has to be closure in so much as it just depends on fluid properties. So the equations are closed. But two is that, yeah, it should try, when it's self-consistently implemented, it should yield a profile that looks something like the black curve, because the black curve is actual experimental measurement of what the effective collision frequency looks like in the thruster. So that is the ultimate goal, that you implement a closure model and it's self-consistently updated. All the fluid equations are solved simultaneously, and it yields a curve that kind of looks like that. And if it does successfully capture that, then all the other fluid properties of interest flow down from there. You can get the ion acceleration correct. You'll get the thrust generation correct. You'll get the efficiency of the thruster correct. The idea is actually
knowing this profile is not sufficient.
Yeah, that's right. So it is not sufficient just to impose that profile. It is sufficient from if you want to make your code match experiments, then if you implement this black curve just spatially implemented in the code, so that in a sense is some sort of closure, you will directly match experimental measurements, but it's not predictive. And that's the key. That's the key distinction there, because this profile changes depending on operating condition. It'll move location or amplitude or even shape to a certain extent.
And are there parts of this curve that are more important? For example, would it be enough simply to get the collision frequency right when it's above, say, 10 to the 8 here, or 10 to the 9 hertz?
Yeah, it turns out that the thruster performance is somewhat insensitive to things that occur kind of upstream of that minimum. It can be important to a certain extent to maybe dictate things like total amount of current predicted for the thruster, but yeah, it's relatively insensitive. So in answer to your question, the most important things to capture are that minimum right there, its spatial location, as well as the 2 to 3 order of magnitude increase that happens subsequently downstream.
And so if you're correct that anomalous transport is due to the electron-cyclotron drift instability, does this suggest paths for improvement?
You mean thruster improvement?
Yes.
Yeah. Ideally, your thruster has no electron transport because this does represent a parasitic loss. Any electrons that are transiting through the thruster don't contribute to thrust. And that's actually the dominant loss process. So it lowers the efficiency by a factor of 25%. So if you could choke off that transport by potentially damping the oscillations, in theory, yes, you could increase the performance of the thruster. On the other hand, you do need the electrons to get across field lines to a certain extent to complete the circuit. So you might run into a scenario where you choke off too much current and the thruster circuit can't complete. But in short answer to your question, yeah, I think there could be ways to try to boost performance a little bit. From a practical perspective, it may not be that necessary because Hall thrusters themselves are about 70% electrically efficient, which is pretty good.
Thank you. Are there other questions?
Yeah, I've got one more. So if you were to simulate this in 2 dimensions, could you capture this effect in like a Z phi geometry, where you just have the cylinder, or do you need to get that radial dimension as well to get the ECDI?
No, so you can do it in Z theta, and people have done that. They've done 2D PIC simulations in Z theta. And you will get the wave to exist in your simulation. The caveat, to me at least, coming more from an experimental background, is that the waves that you get from those simulations do not look like what the actual waves look like in the plasma, in the experimental plasma. And as I kind of mentioned in the talk, I think it's still an open question as to why that's the case, but it seems to be that three-dimensional effects are important for dictating what the actual spectrum will ultimately look like.
Thanks.
Other questions?
Yeah, I have a question. This is Daniel Main. In terms of 3D pick, which you mentioned, and the difficulty of doing that, do the constraints come in with just doing the Monte Carlo aspect and getting all the collisions in that are needed to maybe capture that collision term, that single collision term that you're putting in, and also resolving the mean free path? Or does the restrictions come in more on the numerical stability side, where if it's a explicit code, you have to resolve the Debye length, but you can get around that with implicit schemes?
Yeah, the short answer is, if you have enough computational speed, I don't think 3D pick is intractable for this problem. And so the reason why it is intractable right now, I think, falls under both camps that you alluded to. To get this effect, you have to model the electron dynamics in addition to the ions, and so that requires very small time steps, effectively. And to be sure, there are people that have recently done 3D pick on a Hall thruster, but it was in a reduced dimensional thruster, so much smaller than an actual thruster, in order to save on computational expense.
Yeah.
So, but as computational resources become more available, I mean, for some of these fusion modeling that they do, the six dimensional fusion modeling, like if you apply those computational resources to a Hall thruster, you could do it, no problem. And I think you would capture pretty much all the physics that are of interest. It's a good point about the inelastic collisions. I don't really have a good sense for how difficult that is from a Monte Carlo perspective, but at least from the ECDI, and that's effective transport, that would all be self-consistently captured just by modeling the electron and ion dynamics.
Mm-hmm.
I think you may have already sort of answered this question, but what is the sensitivity of Hall thruster performance to anomalous transport? I think you said there's a 20%, 25% efficiency loss due to anomalous transport. Does that mean that predictive capability of modeling is good to about 25%?
No, it just means that the effect of the transport is to lower the performance by 25%. But in terms of prediction, the kind of the golden standard for prediction for Hall thrusters is not the performance itself, it's the distribution of the plasma spatially. And in particular, I don't have any profiles shown here, but we can measure experimentally how rapidly the ions accelerate and to what speeds. And the gold standard for evaluating Hall thruster predictive capability is how correctly can you capture that profile. And that profile is extraordinarily sensitive. Very small tweaks to the anomalous collision frequency can vary that profile quite precipitously. So I don't have a good figure of merit for it off the top of my head. We actually have tried to quantify that recently through a paper that's in review. But yes, the takeaway is that it can be orders of magnitude, not 25% variations if you get the anomalous transport wrong in terms of that ion velocity profile.
Thank you. Our hour is almost up. Is there a last question? If not, then Ben, I want to thank you again for a fascinating and very well put together talk.
Well, thank you again for the invitation, Greg, and I hope to see you in person again at the next conference.
I look forward to it.